the sun brings out a sex appeal.
In this chapter we have 3 different exercises that need to be solved. The first one asks, what happens to the frequency of the pendulum if it's taken from the sea level to the top of a high mountain and started at the same angle of 5 degrees? Would it oscillate faster, slower, at the same frequency? What would it do? So we know that the period of oscillation for a simple pendulum is 2 pi times L over G. L is the length and G is the acceleration of Earth. So as we go from sea level to the top of a mountain, we are further away from the center of the Earth, which means that our G would be less. Not much, but slightly. That means that the period would go up. So that means that it takes a little bit longer for it to swing back and forth. So at the top of the mountain, it will oscillate slightly slower. The exercise I asks us to return to the opening question in page 369 and answer it again now. So the question was, if pendulum is suspended by 5 degrees and then you measure the frequency or period, and then you compare it to the case where the initial angle was 10 degrees, would it take longer or same amount or less time for the pendulum to swing back and forth? So in essence, they're asking what happens to the period of the pendulum when you change the initial angle. Well, if you look at the expression for the period, we see that there is no dependence on the amplitude. So the amplitude has nothing to do with the period. So these 2 pendulums would swing back and forth exactly in the same time. You might have answered differently to start with, because it's intuitive to assume that in this case the trajectory that it has to travel is much more. But also when it swings further away, the restoring force, its magnitude, increases. In fact, in such a way that it perfectly makes up for the extra distance. So these 2 pendulums will swing with the same period and same frequency. Then the last one, exercise J. Part A. Estimate the length of a simple pendulum that makes 1 swing back and forth per second. So the period would be 1 second. Period is 2 pi square root of L over G. And we have to solve for L. So we raise to the second power 4 pi squared L over G, and L will be T squared times G divided by 4 pi squared. The frequency or the period was 1 second, so 1 second squared times acceleration of gravity at sea level, we assume 9.8981 meters per second squared divided by 4 pi squared, and this is about 0.25 meters. Then part B, what would be the period of a 1 meter long pendulum? So period would be 2 pi L over G, 2 pi, length 2 meters divided by length 1 meter divided by 9.81 meters per second squared. And this turns out to be quite exactly 2 meters.
These are the good times in your life, so put on a smile and it'll be alright. These are the good